So good afternoon. This is NE 429, which is Propulsion System Preliminary Design. And this is a sponsored project from Honeywell Aerospace down in Phoenix. And with that, I'm going to turn it over to Ariel Neville, who is the design team lead for the project, and she'll introduce you to the project and introduce you to the team. Okay, thank you.
Hello, my name is Ariel Neville, as stated by Dr. Haven, and I am the design team lead of the Simulated Environment Experimentation ++ team, and we are the third iteration of the Honeywell project. Today I am joined by my design team, which includes our two different sub-teams. The first is the design and fabrication team, consisting of Mr. Matthew Jones and Mr. David Small, as well as the instrumentation and data analysis team, consisting of Mr. Aaron Butler and Mr. Aaron Parker. I would like to thank and acknowledge our generous sponsor and mentor, Dr. Alexander Mirsamharyan, and his colleague, Mr. Jacob Harding, who are in the audience today. I would also like to thank Logan, Alan, and Christian of the previous C teams for their continued support for the continuity of this project, as well as the following Embry-Riddle faculty: Dr. Haven, Dr. Haslam, Dr. Fabian, Dr. Skipper, Professor Helbling, Professor Zwick, Mr. Clauser, and Mr. Davis. Today in the presentation, we'll be beginning with our project scope and requirements, and then continuing from that introduction with our rig design approach and performance ability. We'll go over the updated stationary and updated rotational rig designs as they have progressed through phase 4 preliminary design, followed by a structural analysis of our rotational assembly and a flow analysis for a 2D turbulent flow model. We'll continue with the data acquisition and sensor requirements integration, as well as a proposed testing matrix for detailed design. Preliminary analysis was done on our ramjet bore, which will provide mass flow to our system, and we'll have data to present on that in regards of pressure, temperature, and mass flow rate. I'll conclude with budget and labor analysis and recommendations for phase 5. And now I'll pass it off to Mr. David Small for project for scope and requirements introduction.
Thank you. The purpose of this project is to design a test rig that simulates a cooling airflow inside a turbine, specifically the airflow through the disc-live rim slot. This image on the right shows the airflow in the red arrows with the disc-live rim slot highlighted in blue. Additionally, we will be measuring, taking pressure measurements in a rotating frame with the sensors mounted close to the axis, which has not been done before in the industry, and so will be a new endeavor. Honeywell's interest in this project is to quantify the flow characteristics in the disc-live rim slot to help optimize how the engine runs, which improves overall engine efficiency. However, the disc-live rim slot cannot be measured where it currently is situated, as is in the high-pressure turbine, and so it rotates very fast and is very small. This image on the right shows the location of Dlrs inside the engine. All of these issues makes it very expensive, if not impossible, to take pressure measurements from the actual Dlrs. To help to constrain our rig, we are given 4 non-dimensional parameters to match. The rotational Reynolds number, which matches the rotational fluid momentum to viscosity. The Reynolds mass flow number, which matches the axial fluid momentum to viscosity via mass flow. The Taylor number, which defines the mode of flow and stability about the axis of rotation. And the swirl number, which is the different ratio between the axial fluid velocity and total fluid velocity. Shown here was the first iteration of IRIS made by the previous 2 teams. This was designed to run at about 3,000 RPM, however it never reached a design point very long. A key note on this rig is the spider tubes located here that take the air from the annulus out to the test sections. Here is our rig design of IRIS. We have extended the annulus all the way out to the test sections, eliminating the spider tubes. We have also added better sealing between the stationary and rotating components to minimize air loss, and have added cross supports between the legs to help with rigidity of the test stand. The benefits of redesigning IRIS are to improve performance. By moving the annulus all the way up to the test section, the same as the image on the right, and eliminating the spider tubes, we are eliminating the possibility of pipe flow before the test sections, and more closely match the inside of a turbine as shown in the picture in the top left. We've also, by improving sealing, we lose less mass flow out the rig in undesirable locations. And this rig has been designed to operate here at Prescott to improve the data acquired when we tested locally here on campus. The deliverables of this project is to give a rig to Honeywell that accurately simulates the DLRS that can be used to collect data. Specifically, we will be collecting data from the rotational frame, which is pressure, and then be collecting pressure and temperature data on the stationary frame, as well as velocity data that will be used to calculate the Taylor and swirl numbers. We will use this data to verify CFD analysis of the test rig and to make sure that we match the non-dimensional parameters. And I'll give it back to Ariel now for rig design approach and performance ability.
Thank you. As David had previously stated, we did redesign IRIS after the first 2 iterations. Importance was placed on 2 of the non-dimensional parameters, including the rotational Reynolds number and the Reynolds mass flow number, excuse me. From there, we were able to design an operational point for the rig as well as dimension it. The first step in our design iteration of IRIS to determine that operational point dimensions was to calculate or determine a baseline atmospheric condition that we would use for the Reynolds numbers, which includes pressure, density, dynamic viscosity, and temperature. We used atmospheric data interpolated for our altitude condition of 5,177 feet from the Fundamentals of Fluid Mechanics book, and that pressure ended up being 12.16 psi, which was deemed acceptable as Ernest A. Lovefield annually records an atmospheric pressure for Prescott between 12.11 and 12.2 psi annually. The corresponding temperature for this pressure is approximately 66.1 degrees, which was chosen because it is also the average high between the months February and April when most of our testing will occur. The corresponding density and dynamic viscosity for the temperature of 66.1 degrees is outlined in the table on the slide. Next, after there was the baseline determination of our atmospheric conditions, we were able to constrain the rig parameters to define dimensions. We defined the outer annulus radius as the center of the drive shaft, which is the center of rotation, out to the most tangential point of the test section. Then the inner annulus radius was defined as the center of rotation from the drive shaft to the bottommost tangential point of the test sections. Therefore, we have a diameter of our test section tubes, which are circular, as the difference between the outer annulus radius and the inner annulus radius. Both of the Reynolds mass flow number is dependent upon the hydraulic diameter of the test tube, and for a circular design, the hydraulic diameter is equivalent to the diameter of the circle or the test section. We also then chose an optimum and maximum mass flow rate per tube of 0.0873 pounds mass per second. And this is per engine specifications of the ramjet blower in the propulsion lab where our testing will occur. Secondly, we also then had to constrain the outer annulus radius to 16 inches. Since we will be reusing the base and the motor track provided by previous C teams, we need to make sure that the outermost radius of the rig does not interfere with the motor or we would have to redesign the base, which was something that the team decided not to do. And so we constrained that to 16 inches. From there, we were able to determine that the inner annulus radius would be 15.25 and the diameter of the test sections of 0.75 inches. Our rotational speed is approximately the same as the previous C iterations at 3,055 RPM, which is just about 100 less than what they were operating at. From those defined operational points and dimension, we have an ability to meet the non-dimensional parameters provided by Honeywell within 27%. More specifically, the Reynolds mass flow number is met at 26.8%, and the Reynolds rotational number is met within 0.05%. After communication with Honeywell, it was deemed that these values are acceptable and the rig dimensions were finalized. Since the previous team had an issue with their rig and being able to pass the mass flow rate because choke was occurring in their test sections or at the entrance of the test sections, we wanted to make sure that this design consideration was kept in mind when we designed and dimensioned our rig. So we did a static 3D station analysis of our rig to determine if mass flow rate could pass through the Dlrs. We defined our rig into seven different sections, the first being the inlet, the second at the entrance of the first diffuser, 3 is the exit of the diffuser, 4 is in the feed duct before the guide vanes, 5 is after the guide vanes at the end of the feed duct, 6 is between the rotating and non-rotating annulus, and 7 is the simulated Dlrs test sections. We assumed for this analysis that there was no mass flow loss through the system. Then, to determine whether or not the mass flow would be able to pass through the DLRS, we analyzed the mass flow parameter, which is defined as the ratio of mass flow rate to the square root of total temperature over area and total pressure. This then becomes a non-dimensional value when you multiply by the square root of the of the gas constant over the gravitational constant. Our mass flow parameter at the DLRS test sections was calculated to be 0.47, and then we compare that to the mass flow parameter at Mach 1, which is where a choke would occur if there were to be a choke, and it's approximately 1.68. 0.47, our mass flow parameter, is less than 0.68. We should not expect a choke flow, and we should therefore have a sufficient area to pass the mass flow. Further from this analysis, we were able to determine areas of which our rotating and stationary components were dimensions were based off of. Further, the team was able to calculate some expected temperatures, velocities, and pressures throughout the test rig. After this analysis, the team will be expecting a pressure ratio of approximately 1.04, and we will be expecting our rig to operate near atmospheric pressures. A sensitivity analysis was then performed so the team could analyze the rig's performance based off of changing of the design parameters. The first variation completed was the effective variation in rotational speed. The rotational speed has no effect on the Reynolds mass flow number, but does moderately affect the Reynolds rotational number. Our design point is highlighted in green, which is 320 radians per second, or just about 3,000 RPM. As you can see, even with slight overshoot or undershoot, we will still be within 11% of the Reynolds rotational number. The second sensitivity analysis performed was the effective variation in hydraulic diameter. Since we constrained hydraulic diameter to be the definition between the outer annulus radius and the inner annulus radius, it also has an effect on the inner annulus size, and so therefore both the Reynolds mass flow number and the Reynolds rotational number will change. Our design point is highlighted in green. All of the design points highlighted in red are invalid solutions as a result of our stationary analysis previously discussed, because there is insufficient area and choke flow will occur, and we cannot pass the mass flow, and therefore our pressure data collected at the test sections will not be meaningful. The third analysis performed was effective variation in the number of test sections. The team has decided to go with 10 test sections, which is the same number of test sections as the previous designs of IRIS. And this puts us within 27% of the mass flow rate. Although you can see that the optimum number of test sections is at 8, for about 9% off of the Reynolds mass flow rate, the team decided to stick with 10 test sections, as it is easier to seal off other test sections if need be, to better match the non-dimensional parameters. And this could potentially be due to atmospheric changes in density and dynamic viscosity on our testing date. The number of test sections less than 7 will result in invalid solutions, as there's insufficient area for choke flow to pass the mass flow. Lastly, the team decided to do a sensitivity analysis on the effective variation in atmospheric conditions. The rig was initially constrained to have that 12.16 PSI, atmospheric pressure, 66.1 degrees, etc. However, being able to actually obtain those atmospheric conditions during a single test day is unpredictable, and we wanted to see how the change in temperature would affect then density and dynamic viscosity, and ultimately the Reynolds numbers. The team has decided that approximately 58 degrees is where we have our optimum operating condition for about 13% off on either of the Reynolds numbers. The team, since we are currently undershooting the Reynolds mass flow number, has decided to optimize for lower temperatures and therefore lower dynamic viscosity. Since dynamic viscosity is a division factor in both of the Reynolds numbers, we should be able to therefore minimize our percent difference between the given Honeywell values and the actual calculated values for those Reynolds numbers. And now I will pass it off to David Small for the updated stationary rig design.
Thank you. There are 7 main component groups in the stationary rig. There's the rib clamshell annulus, shown in yellow, the dual brush seals, the diffuser cone, shown in green, the front bearing assembly, shown in blue, the guide vane assembly shown in purple, front leg assembly and supports shown in orange, and the rear leg assembly and base with the base shown in red. The first component group is the rib clamshell annulus. This will be composed of 7 different pieces that will be bolted together. The pieces are diffuser 2, the feed duct, which is designed to hold the front bearing assembly and therefore the drive shaft, diffuser 1, and the inlet. The dimensions give an overall length of the annulus of 42.47 inches. The annulus will be fabricated from rims and flanges, as can be seen in this half-scale model held by Matthew Jones. Ribs and flanges will be cut from A36 steel that is 1/4 inch thick, locally here on campus using our water jet cutter. We will then cut a wall out of 20 gauge 304 stainless steel that we will weld into the annulus to give a smooth airflow area. All of these pieces will be welded together to give rigidity. The second component is the dual brush seal. This consists of a 3-piece holder that will hold 2 brushes. There will be 30 pieces of the brush holder that will be 3D printed using PLA plastic, and then 2 brushes that will be nylon and polypropylene. The holders will be bolted together to hold the brushes, and then the holder will be bolted to the annulus. The design of the holder is such that it fits snugly to the annulus. The third component is the diffuser cone. It is made out of 3D printed PLA plastic, and its dimensions are based on the requirements mentioned earlier. Fourth component is the front bearing assembly. This contains 2 ERAU-32 insert bearings, which allows us to impart a moment to the drive shaft, minimizing deflection of the drive shaft due to the rotational component's weight. The bearing housing will have 2 grease ports to allow maintenance of the bearings, and the housing supports will have an aerodynamic shape to minimize the disturbance to the airflow. The bearing housing will be turned from a 4.5 inch outer diameter steel tube with a 3 inch wall, and the housing supports will be made from 1 inch by 3 inch steel bar that will then be welded to the bearing housing. The fifth group of components is the guide vane components. We are adding the ability to add guide vanes to the rig at a later point if deemed necessary based on the Taylor and swirl numbers. This design allows for easily insertable vanes that will slide into a slot and then will be held in place by a lock ring shown here. On the back of this assembly is a hatch that allows access to the bearing, one of the bearings, so that we can make sure it is attached securely to the shaft to decrease wear on the bearing. The sixth group is front legs and support structure. We will be making new front legs to match up to the feed duct of our new redesigned annulus. And then we'll be adding a cross support between the legs to help add rigidity to the support structure and to allow adjustment in the pitch of the annulus as shown in the image on the right. This will allow us to optimize the placement of the sealing to minimize the air leakage between the stationary and rotating components. And all of these components will be made out of A36 steel and either welded or bolted together. The seventh group of components are the rear legs and base. We will be reusing the rear legs and base from the previous team. However, we will remove the slip ring mount from the rear legs as we will be designing our own slip ring mount. The base, which is made out of concrete, includes the motor and motor track system. However, we will be modifying by adding additional wood supports underneath to allow the use of a pallet jack to move the test rig around. Now I'll pass it off to Matthew Jones for the updated rotational rig design.
There are 4 main components in the rotational assembly. There's a large disc, a support disc, 10 identical test sections, and an inner annulus. These components can be seen assembled onto the drive shaft in the picture on the right. The first component is the large disc. This disc must retain pressure, it must secure the entrance to the test sections, and it must provide a surface area for sealing. To accomplish this, we have a 36-inch diameter disc, which gives us 2 inches around the circumference for the brush seals to seal against. The disc has a solid center, which allows it to retain pressure, and there are 10 holes around the circumference which serve as the entrance to the test sections. It has a central 2-inch diameter hole so that it fits onto the drive shaft. This disc will be water jet cut out of 6061 1/4 inch thick aluminum plate using the water jet here on campus. The second component is the support disc. This disc does not have to hold pressure, which allows us to cut additional holes into it to make it lighter. This disc does not have to provide sealing, which allows us to make it overall smaller, giving us an overall diameter of 34 inches instead of 36. The main purpose of this component is to support the back end of the test sections. For this purpose, we have 10 1.25-inch diameter holes around the circumference so the test sections will fit through it. And this component must also be easily allow sensors to be mounted onto the test sections. Similar to the large disc, this will be water jet cut out of 1/4 inch thick 6061 aluminum plate. The third component is the Dlrs test section. This test section must have a uniform interior geometry so as to not skew the flow as it passes through. It is also desirable for this piece to have a thick wall so that we can tap it and mount sensors easier. This tube will be a standard size with a 3/4 inch inside diameter and a 1/4 inch thick wall. We'll be using aluminum tubing, not only due to the weight and the fact that it matches the large and support disc, but also due to the fact that aluminum tubing natively has a uniform interior geometry. Fabricating these will simply require cutting a large section of the tubing into 6-inch lengths, then drilling the holes and tapping. The fourth component is the inner annulus. It is very desirable to have this annulus have as minimal a deflection as possible, as any outward deflection of this component will reduce the area that the flow sees and passes to the test sections. To mitigate the deflection, we have design in the area here, meaning giving us a total thickness of just over 2.8 inches thick at this location, where it will interface with the large disc. Ansah simulations have shown that this is a load-bearing component, which the thickness will also help with. The small end of this component will interface with the feed duct, and the large end will be tangential to the holes in the large disc. Due to the complex geometry, this component will be 3D printed using PLA plastic. In order to fit it onto a MakerBot replicator, we had to break it into a total of 60 different pieces. These pieces will be carefully sanded until they fit together and then epoxied together to form the piece. Once it is complete, the outside surface of the flow sees will be smoothed, and then it will be attached to the large disc using epoxy. I'll now continue into a structural analysis. To ensure that the rotating assembly can survive at our design point of 320 radians per second, we have conducted Ansah simulations. This image shows the total deformation plot of the rotating assembly, magnified by 44 times so it is possible to see the deformation. The maximum deformation occurs on the inner annulus and is approximately 40 thousandths of an inch. This reduces the area by approximately 6%. Communication with Honeywell has indicated that up to 10% is tolerable, which means that this design is acceptable. This plot shows the maximum total deformation as it relates to RPM. It is important to note that this can be modeled using a second-order polynomial, which means that as RPM increases, deformation will significantly increase. This image shows the maximum principal stresses of a rotating assembly. Maximum stress occurs where the test sections meet the large disc. This max stress is approximately 25 KSI. The yield strength of the 6061 aluminum that will make up the large disc is 40 KSI, which gives us a factor of safety of approximately 1.6. On the inner annulus, the maximum stress is only about 2 KSI, and the 3D printed PLA plastic can handle up to 8 KSI. This gives us a factor of safety of about 4 on that component. To verify these Ansah simulations, we have created a proof disc. This disc is 30 inches in diameter, has a 2-inch central hole, and only rotates at 200 radians per second. Hand calculations, which use a slightly conservative method, estimated the maximum stress at approximately 5,500 psi. An Ansah simulation of this disc estimated the maximum stress at 5,000 psi, which yields an 8% difference relative to the hand calculations. And a CATIA simulation estimated the maximum stress at 4,600 psi, which is a 17% difference relative to the hand calculations. Due to the weight of the rotating assembly, we are expecting noticeable shaft deflection. The rotating assembly weighs approximately 130 pounds. We have a variable length between our front and rear legs to account for fabrication tolerances and any unforeseen issues. Our minimum drive shaft length will be 32 inches. Our maximum will be 37 inches. At the minimum length, we can expect about 7 thousandths of an inch of deflection, and at the maximum, we can expect about 11 thousandths of an inch. I'll now pass it to Ariel Neville for flow analysis.
The team has decided to begin work on our computational fluid dynamic models for the air passage flow through the test section, and this is to determine the effect that our geometry will have on flow behavior. The first simulation that was run was an initial 2D static turbulent flow analysis. The pressure contour on the left measures in static gauge, PSI, and specifically knows 3 different stagnation points. The first stagnation point is at the entrance to the diffuser at that tip, and that is simply due to the nature of the diffuser cone. The second stagnation point occurs at the end of the diffuser and along the beginning of the feed duct. This stagnation point is characterized by a sharp increase in pressure and can be reduced by adding a fillet to the ribbed annulus. The third stagnation point is at the entrance to the Dlrs test section, and this has to do with the turning of the flow. So the flow is going to be going through the rotational and stationary walls and then making a sharp turn into the Dlrs test section, where it will see a significant pressure increase before going through the test section. Also in the rig, between the end of the feed duct and the beginning of the rotating and stationary walls, you can see a pressure contour where pressure begins to significantly decrease over a decreasing area, and this indicates a potential vena contracta. There's also a potential secondary vena contracta that could potentially appear in a 3D model at the beginning of the test section due to the fact that the inner and outer annulus area decreases as it enters the test section. The velocity contour on the right also characterizes that potential vena contracta at the end of the feed duct. And this is because you can see that the flow experiences an acceleration through a tightened area and the velocity is increasing. Second from the velocity contour, you also notice that there is developed pipe flow through the Dlrs, characterized by a lower velocity through the boundary layer. The team is expecting this pipe flow to diminish or decrease significantly as the 3D model is developed, and also due to the turbulent nature through the Dlrs test section. And now Aaron Parker will discuss data acquisition.
Thank you, Ariel. In order to fulfill the project requirements, we were required to take data from both the rotating and stationary frames of Iris. One of the most difficult challenges in this is taking data from the rotating frame, as it rotates at upwards of 3,000 RPM. The first challenge in doing this is providing power to both the sensors and other components in the rotating frame. This is most easily accomplished through the use of a slip ring. The specific slip ring we have chosen is the Mercotec 205H. It was chosen for its 2 channels, which are enough to provide power and ground, as well as for its maximum RPM of 3,600, which is enough to give us a factor of safety over our design point of 1.178. It was also chosen because it is fairly inexpensive. The slip ring is seen in the pictures to the right. In order to use a slip ring, we need to mount it. The recommended mounting configuration is shown in the picture on the left. This was provided by Mercotec. What this shows is that the main body of the slip ring is held by a rigid mount, and the rotating side of the slip ring is held by a vibration dampening mount. While our rigid mount and an alignment tool are still in development, we have designed our rotating mount. This involves welding a 1/4 inch thick aluminum disc to the end of our shaft, and in the center of this disc will be a hole for passing wires through, and also in the center, a 3/8 inch aluminum pipe will be welded. This aluminum pipe will go inside of a rubber tube, and this rubber tube will hold a rubber gasket that holds the slip ring. This should dampen vibration and also allow for some mitigation of eccentricity. Once the power goes through the slip ring, it will power a microcontroller. This microcontroller will then power our sensors, read the analog outputs, convert them to digital, and store them on a flash drive for removal after the test is complete. The specific microcontroller we have chosen is the Arduino Do R3-E. It was chosen for its 15 usable analog to digital converter channels, which will, again, convert the analog signals from the sensors into digital signals to be stored on the flash drive, as well as for its one native micro USB port. This allows it to easily interface with the flash drive we have chosen. This microcontroller runs off of up to 9 volts, which is more than enough to provide power for our sensors. In order to use this microcontroller, we have to mount it in the rotating frame. As such, we have designed a mount that will sit between the support disc and the rear bearing. This is shown in the pictures to the right. This will support both the microcontroller and the storage device at our design RPM, as well as provide easy access to the storage device. It also will provide access to the sensor ports for wiring the sensors to the microcontroller, and will have a balancing compartment to which weights can be added in order to balance the weight of the microcontroller. Finally, in the stationary frame, we will be using the National Instruments SCC 2345 Data Acquisition Unit, or DAC, in order to take our measurements. We will be using an FTO1, or a feed-through module for a mass flow meter, and a TCO2 module for a thermocouple, or several thermocouples. I will now pass it off to Aaron Butler for sensor requirements and integration.
Thank you, Aaron. Iris will be split up into 4 test sections to measure pressure and temperature, as shown in the figure on the right. At Station 1, we will be mounting a mass flow meter and a thermocouple between the ramjet blower and the inlet duct of Iris. At stations 2 and 3, we will be implementing a potential ultrasonic anemometers. This will be placed before and after the vena contractor. It would also measure velocity. At Station 4, we will be again measuring temperature using a thermocouple at the test sections. To measure pressure, we will be using static and dynamic pressure transducers. And finally, to calculate total pressure, we'll be using 5 pitot tubes. The pressure data collected at the test sections will be used to quantify the characteristic flows inside the test sections, but also to help us calculate the mass flow at the test sections. And then we can compare the mass flow at the inlet and determine any possible leakage in the rig. We'll be using 3 stationary instrumentation, the first being a mass flow meter, the Sierra series mass flow meter. We are expecting a mass flow of 860 standard cubic feet per minute, which translates to 0.873 pounds mass per second. The second instrumentation we'll be using is the Type T thermocouple. We'll be using this thermocouple to collect dynamic viscosity as well as density. From there, we'll be able to use these values to calculate the Taylor number, the Reynolds mass flow number, and the Reynolds rotational number. And lastly, we'll be using the previous team's Monarch optical RPM sensor. This will help us calculate the velocity at the test sections, which will then ultimately help us determine Reynolds rotational number. The optical sensor will be placed at the rear supports of Iris. To measure static and dynamic pressures, we'll be using a printed circuit board Honeywell pressure transducer used from the previous team. Again, we chose this because we can measure a maximum pressure of 30 psi, but also it's very lightweight and it's very cheap to implement. From using the previous C team's pressure transducers, we were able to test the voltage, differential voltage using ambient atmospheric pressure, as you can see from behind me. One thing to note is we found that one of the pressure transducers was non-operational due to poor connectivity between the wires and the PCB. So therefore, to reduce the error, we decided to eliminate the PCB pressure transducer board, and then instead directly mount the pressure transducers. Behind me is the current proposed pressure transducer mount. As seen on the left image is the exploded view, and then on the right is the fully assembled view of the mount. The mount is capable of holding up to 15 pressure transducers. We can hold up to 3 pressure transducers at the site, which will then be directly aligned to the pressure tapped holes at the disc-like rim slot test sections. On the image on the right shows the placement of the mount. It is between the rotating discs. To connect the pressure transducers to the disc-like rim slot, we'll be using our own custom pipe assembly, seen here. It will consist of automatic braking, right here, and a plastic tubing, right here. These will be connected using compression fittings, but also male and female barbed hose fittings. And it will be directly mounted perpendicular to the test sections. I will now go on to testing proposal. The testing proposal. There are 2 phases for the testing proposal. This will ultimately determine the rig's structural survivability, but also the instrumentation. There is a total of 7 testing iterations. During phase 1, the first test iteration, we'll be conducting blower testing to determine the behavior of the blower and with the unknown back pressure. The second test iteration is the rig survivability, where we will bring the rig up to optimum RPM. However, we will not be turning the blower on. For the third test iteration, we will be testing the stationary instrumentation with no rotation, but we will be turning the blower on. And lastly, for the 4th iteration for phase 1, we'll be testing the pressure measurement instrumentation with no blower, but we will be bringing the pressure instrumentation up to full optimum RPM. During phase 2 of the testing, we'll, for test iterations 5 through 7, we'll be collecting pressure measurements at our RPM, optimum RPM, as well as turning the blower on. I will now pass you on to Aaron Harper, who will talk about preliminary blower data.
Some of the first testing that we did was testing of the blower. We did this to verify that it can provide the mass flow that we need to run Iris. This is our testing setup. The blower is connected directly to the mass flow meter, which has a gate valve on the other side. This was implemented to provide an artificial back pressure to simulate as if Iris was attached to the other side of the mass flow meter. In the first part of our first test, we did a mass flow test with no back pressure, as in the gate valve was completely open. As you can see, the mass flow quickly stabilized and remained consistent throughout the entirety of the test. We then did a performance analysis on this test and found that our percent difference was about 38.09% on the Reynolds mass flow number and 0.05% on the Reynolds rotational number. This was because although we assumed our design point density and viscosity, we assumed that the ambient pressure and temperature would be coming out of the blower. Then we did a test with a previously determined minimum area to provide that back pressure. As you can see, it stabilized over the course of about 5 seconds, and then after about 10 seconds, the blower stalled and the test was aborted. Once again, we had about a 38% difference from the Reynolds mass flow number and a 0.05% difference from the Reynolds rotational number due to those same assumptions. The second test, we tested the mass flow meter as well as a thermocouple for 45 minutes. In this test, it quickly stabilized. However, as you can see from the spike there, a piece of tape came loose off of the thermocouple and got trapped on the mass flow meter. However, once it blew out, the pressure, the mass flow restabilized and continued to be stable throughout the rest of the test. We also calculated the total pressure and static pressure. These look extremely similar, one's just slightly offset due to the fact that they're related through the Mach number. And once again, you can see the effect that the piece of tape coming off had. These also remained at slightly above atmospheric, which gives us close to our pressure ratio of 1.04. We also graphed the temperature versus time. Originally, the temperature was around 60 degrees. However, it quickly climbed to about 95 degrees and stabilized there. This was higher than we expected, which led to this percent difference calculation. These percent differences are obviously much higher, with a maximum of 66.4% difference. This was because we were able to calculate the viscosity and density, and the increasing temperature adversely affected these. This resulted in not only the percent difference change in Reynolds mass flow and Reynolds rotational number, but also a far lower mass flow. I'll now hand it off to Ariel Neville for budget analysis.
Honeywell has allocated a total of $5,500 for this project. The amount spent to date is approximately $1,400. The majority of that cost has been in purchasing the material, including steel, stainless steel, and aluminum for the project. We have allocated approximately $600 for the annulus and rig construction hardware, and the PLA 3D printing for components such as the diffuser, the annulus, the rotating annulus, the guide vanes, and the brush holder. This gives us approximately $3,400 heading into detailed design for unexpected costs, as well as upgrading our instrumentation. I will also now discuss the labor analysis performed through preliminary design. Our actual hours worked is highlighted in green on this graph, and the predicted hours is highlighted in blue, and it has remained constant because the group had agreed that despite holidays and breaks, we would put in the same amount of hours per week that was expected on total weeks due to the enormous project scope. As you can see, starting from week 2, we have been steadily above our predicted hours. The team has logged a total of 1,135 hours throughout the course of this semester. Starting from week 2, we significantly increased our counted over hours over our predicted hours by approximately 60. I will now conclude this presentation and provide the audience with some of our recommendations for detailed design. From this presentation, you have seen the development of the CATIA model. However, this does need to be improved to include the Arduino mounting as well as our pulley and tensioning system, so we can prevent belt slippage from the drive strap to the motor, as well as include our pressure transducer lining that Aaron Parker described with our automotive brake line, which is currently not included in the CATIA model. Further, we have defined several of our rig subsystems, including our leg assembly with the adjustable mount to aid in the mating of the brush steel to the large rotational discs. However, we also need to confirm our pulley tensioning system, which will be reused from previous C teams. However, due to some continuity issues in determining the belt length, we will have to redo some of these calculations and purchase a new belt. As well as Aaron Parker had also described that we need to complete the 5 degree of freedom rigid stationary mount for the slip ring in order to reduce the eccentricity of the slip ring alignment to less than 5%. We also have begun a rotational Ansah simulation. However, this does not include other rotational components such as the pressure transducer lining or the drive shaft. It would also be beneficial to the group to expand the Ansah simulation to our stationary system, particularly the leg supports, as it will be under heavy loading from the large rotational discs components. Further, we have begun our 2D static turbulent flow model, and upon verification of these flow characteristics, we will use this as a baseline for development of our 3D stationary and rotational CFD models. to help us better understand the expected flow performance, and then later be able to confirm our data collected with computational fluid dynamic models. Further, we have determined that we would do a power transfer and data transfer through the Arduino for our rotating frame rather than use such thing as a slip ring method. So the slip ring would power the Arduino, and then the Arduino would further power the sensors and collect the signals from the sensors and convert them into a digital. However, we still need to confirm that the Arduino's ADC converter is working and that we can collect data and actually store it onto the USB, which involves some programming. Our preliminary blower analysis has shown us that the mass flow is incredibly affected by the atmospheric conditions of our testing date. And due to this and the changes in dynamic viscosity and density, we will need to reconsider the atmospheric conditions for each of our testing dates and then make redeterminations of rotational speeds, or for example, the number of test sections to better match those non-dimensional parameters. This may include a cooling loop for the incoming air to the test rig. During phase 4, the team hopes to have the complete fabrication of Iris completed by the end of January and beginning of February. This includes implementing the slip ring mount and the pressure sensing tabs that were previously discussed in the presentation. We also are considering and working to implement a disc braking system for the rig to improve its safety procedures. Upon completion of the test rig, the team will be statically balancing the rig before hiring a prop balancer to come out and dynamically balance the rig. Upon completion of balancing the rig, we will do a vibration analysis to determine potentially harmful rotational modes for operation. Further, we will continue to refine our test matrix and complete the necessary testing to determine and confirm the rig survivability and performance values. We'll be able to meet our project scope and deliverables by quantifying total dynamic and static pressures, as well as quantifying the mass flow rate from the simulated Dlrs. All of this data will then be used to confirm that we have met our design performance parameters. And this concludes our presentation. Thank you for your attendance. Are there any questions?
Does the inlet to the test section need any campering or anything? How does the real disc live rim slot, how is that hole straight in off of the face, or is it that tailoring on it on the real one? You have to kind of match that, it's a flush face with a hole, or they've got kind of it's not really a cylinder on theirs. But what I'm wondering about is being a contractor up at the top for what you're trying to do. Do you have to do any type of surface treatment at the entrance to your tube to make it a smooth transition as you go from this direction to that direction and potentially a local acceleration?
In our model of the Dlrs, it would be beneficial, if possible, to include a fillet at that location. As you can see, there was a stagnation point there, so there is a change in velocity. And an actual disc live rim slot, it's an actual slot, so that rotating and non-rotating wall actually exceeds past the Dlrs. And so that's where the hydraulic diameter would come in.
You show the picture.
Try 6. What you want? Or you want one with like 7?
Slide, yeah, 6. 6 or 7. Yeah.
So in that figure, the green line represents the boundary between the non-rotating and rotating walls. And as you can see, the Dlrs in blue is that boundary actually extends past.
Is it curved at all in the real life one, or is it actually a sharp edge?
Well, it's exactly normal to the annulus, so the flow has to turn 90 degrees in. And the slot actually is not circular. It's like a
crescent.
smiling, crescent type shape. And there is a loss there that we account for. But in their case, so we're just straight into their test section without. So, I mean, if we wanted to simulate that, that would be something additional. The important thing in this is just to be able to measure the pressure.
And the last team struggled with the pressure transducers under rotational window. So you guys, there's going to be a window of having a fun time figuring out how much of that's real pressure and how much of it is diaphragm pull from rotational speed. So you'll be spending a lot of time sorting that out. Hopefully Logan's giving you some warnings from the past. Okay?
You said the last team has some time, or a hard time maintaining the rotational speed, maintaining 3,050 RPM.
Our rotational speed is 3,055 RPM, and their design rotational speed was 3,176.
Okay. So it's a little, you kind of cut back a little bit to be something that you feel like you can maintain easier?
The original rig was designed based around sea level values, and so when they did their iterations in the design process, they used sea level density and viscosity, as well as assuming at sea level pressures. However, at 5,177 feet, the pressure is reduced, and therefore there's a significant change in the density and dynamic viscosity. So when we redid that analysis, we ended up coming out with a lower rotational speed, just from the change in the atmospheric conditions.
And then one other comment I had, go like to slide 41 or 43. When you're showing those contours, it'd be nice to have the scale with that, so we would know what we're looking at as far as water body.
The main question I have, maybe this wasn't made very clear to me. The purpose of the experiment, is this to try and duplicate Honeywell's data, or is this to try and supplement their data on the whole?
Honeywell gave us 4 non-dimensional parameters with values that we needed to attempt to match. I don't actually know where those numbers had come from because this project had passed through 3 different years. So we have those numbers to match, but the data will then be used to help Honeywell determine how to actually collect pressure measurements and mass flow measurements in an environment such as the Dlrs.
Well, just to elaborate on your question, those non-dimensional numbers are engine related. That means we looked at our engines, and that's the similarity of the actual engine. So their rig is to simulate those non-dimensional parameters so that the flow conditions are similar. But the main task for that similarity is to measure the rotating pressure. Okay.
That's pretty clean presentation. The brake lining one, Aaron, what are you trying to do? Are you trying to reach out there and maintain position on the tap back to your sensor?
Yeah, we're trying to preserve the flow. Because the previous team used surgical tubing, which had a lot of kinking, which had a lot of flow irregularity. Sorry, and it caused some kind of weird things with the pressure data. So we thought we'd just bring the brake lining and surgical straight up, so we have a perfect pipe flow, so we can record pressure and data cleanly.
The automotive brake lining was mostly chosen because under high rotational speeds, we shouldn't expect it to be kinking. So that's good.
Also, part of the issue was that, again, when it was spinning at that speed, the hoses were kind of going all over the place a little bit until they were zip tied in place, which caused that kinking. With this, it brings it straight down from the test sections, and when we do tests without the blower on, we will be able to quantify the pumping effect down that test section and take it into account when we do our actual tests.
Go through your slide 47. No, 67, sorry. Okay, sorry, go back. 47. Okay, so this analysis was done stationary.
Yes.
Okay, so your pressures are in gauge pressure?
Correct.
Static gauge, so they're very small.
Correct.
Okay, so now the question becomes, when you rotate this, is that gauge pressure the delta's gonna increase?
I don't actually know the answer to that question at this
But you
time.
have that in mind too.
Yes, we are going to be rotating that model. As of right now, we're still learning how to rotate a model over a three-dimensional model.
And the reason why I'm asking that is because that could determine the accuracy on your pressure readings. So we want to make sure that delta P, in this case the gauge static, you'll be able to pick up, or that sensor will be able to pick it up. Okay, that's one question. And the other question is, on the deformation, the 40 mils deformation. I think it would be number 42. 41, yeah, okay, so this, how is, did you use this sensitivity, 40 mils, to see how that's going to impact the flow?
That hasn't been done yet.
So looking forward to your next semester test results.
No, we have considered using that deformation and put it into the CFD model. It just hasn't been done yet because it took us a while to actually develop that 2D static model. And then we came up to this presentation and unfortunately ran out of time.
Yeah. I mean, you have the results, so you could use it now.
Yes.
What's the gap height at that point in max deformation, as you go up that annulus?
So since we defined the test section diameter as the difference between the outer annulus and the inner annulus radius, and for our analysis, we made it a constant gap. It's 0.75 inches. It's the same height as the test sections.
Just give us an idea of how.
Right, or magnitude, right?
Yes.
So if you have that constant gap between the inner and outer annulus, that's going to give you a varying area.
Yes.
How do you intend to account for that when you do calculate the Taylor number?
We're still trying to determine how we're going to calculate the Taylor number. At this time, the importance was placed on the Reynolds mass flow number and the Reynolds rotational number, and that's how the team has determined sizing and rig operation point.
Yeah, well, the Taylor number will apply to the test section. So the deflection there, I guess that's a different color. That's a low color. That's a smaller deflection there. It's not red. Good, which is good. So,
There's almost no deflection at that point because that's where it will be fixed to the
right.
disc.
Okay.
Lots still ahead.